recording. I didn't give you guys a warning. Sorry. Ah.
I don't know why I'm holding this with my left hand. Retarded. I feel like I've heard you say that one.
Yeah, what do you guys think? Should we do just only on Zoom on the 12th, on November 12th? Save you guys a trip in, but also me a trip in. I'll be upfront about that.
I'm still gonna have to come in anyway, but so could we just like have that door not unlocked? That'd be nice. Wouldn't it?
I know, it's weird, but
So is there? You push that little button on there. Does it do that?
no, then I lock myself out.
Oh.
It's like a safety thing.
Oh, okay.
Yeah. It's like you can lock it so no one can access it, but you can't unlock the door.
Oh,
It's weird.
We finished chapter 3 today.
We are going to finish chapter 3 today. I know. We kind of skipped a few things in chapter 3. Because chapter 4 is arguably more important. Mhm.
Yeah. I always like it's starting and I'm like, oh, it expired like yesterday. There's something tonight, right?
Probably. I usually make them do at least a week later.
We don't even have a lab on that Tuesday, actually. So.
Well, that's what we were saying. So because of that, review from last week. I'll keep those notes. We'll talk about them so that we can review them. But yeah. Are we ready to pull the trigger on the 12th?
Yes.
November 12th, Zoom only. Don't come in, just go on Zoom. How about that? And then if you want, you can watch the video after, obviously. But
it's like YouTube, so you can change the speed to like 1.5.
I mean, I put them on YouTube, so yeah.
Yeah, some of the videos you hear, you just have to watch normal speed. And I'm like, oh,
Yeah.
no.
Yeah, imagine the past 4 minutes, just like us blabbing.
I can't do videos on 1.5. I usually do. I process it better too.
I always watch regular speed and it drives my husband bonkers. He's like, you can speed that up. I'm like, no, I can't. Can't.
That's why I listen to our assignment to hydrology. It takes forever, right?
The last section in chapter 3 that we're doing is on rational functions. We introduced rational irrational functions. Well, if we could summarize an irrational function, we'd be rich. So a rational function is when we have a polynomial in the numerator and another polynomial in the denominator. And so, of course, we could let these polynomials be boring polynomials, but we will not, except when we introduce these things. And so just some terminology that I need you to have under control is the numerator is the one in the top and the denominator is the one in the bottom. What does it mean to have a polynomial? It's any group of terms being added together with x's, ax squared plus bx plus c, that kind of thing. It's a quadratic.
That'd be so right.
So we know that we can't divide by 0, right? And so one of the problems that we're going to have is, well, this denominator, this q of x can't be 0. So any value that makes q of x 0 is not in the domain. So then we had to look at this function, the reciprocal function 1 over x. 1 is a polynomial. It's a very boring polynomial, right? What is technically 1? Let's see here. 1 is really 1 times x to the power of 0. That's a super boring polynomial. Anything to the power of 0 is 1. So 1 times 1 is 1, boring. X, not much better, but it is still 1 times x to the power of 1, another polynomial. Very boring polynomials, though. We're going to expand these. But what we need to remember is we can't divide by 0, right? We know that from domain work that we've done before. And so x equals 0 is not in the domain. What that ends up looking like in terms of the graph is this vertical asymptote at x equals 0. So any value that makes us divide by 0 creates a vertical asymptote. Let's see if I can keep pulling this off. Keep up with the projector. It needs to keep up with me. So then what we said was, okay, we need some way to describe this behavior, right? This general behavior around the asymptote, right? Because if we have a look at the difference between 1 over x and 1 over x squared, whoa, here, right? The difference is that these are both positive, right? And so now what we're going to say is we're going to use this kind of, not notation, I guess, but kind of. As x goes to 0, 0 being the vertical asymptote, from the left, we use a negative, right? So from the negative side, so here, as x goes to 0, so as x goes to 0 from the left, we never reach 0, but what happens to the function? The function is going to negative infinity, right? It's going to head down, and it's never going to touch that x equals 0 line. That's what makes it an asymptote. Now, as x goes to 0 from the positive side or from the right, okay, then the function is going to positive infinity. Okay? So we can describe that end behavior by as x goes to 0 from the left, f of x goes to negative infinity. And as x goes to 0 from the right, f of x goes to positive infinity. Same thing here, but as x goes to 0 from the left, it's going up, 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 up. Same thing from the right. So for both of these, as x goes to 0 from the left, f of x goes to positive infinity, and from the right, f of x goes to positive infinity. X equals 0 is still a vertical asymptote, right? Because 0 squared makes 0 in the denominator, so still x equals 0 is not in the domain. Okay. So we're going to look at these vertical asymptotes and see. Now we're going to do these problems here. And let me just clean this up a little bit here. Copy. I'm going to put them on a fresh page, I think. Okay. We've got a little bit more of a grown-up polynomial over a polynomial, so a rational function. What's nice is we recognize both of these, right? X squared minus 4, that's a quadratic. I know how to find zeros or roots of a quadratic. You know what? I will sit down. X squared minus 7x minus 8 is also a quadratic. So I know, I remember, say it with me, I remember the quadratic formula. No, I remember it exists. and then it's on your formula sheet. But the quadratic formula
In the calculator.
is also in the calculator. So all you really need to do is be able to recognize a quadratic, and then you know how to solve for where this thing equals 0. But negative b plus minus the square root of b squared minus 4ac over 2a. I still haven't looked up the song. I guess there's a song, but I already know it, so maybe I don't need the song. But there is a song. So what do we want to do? If we want to find the vertical asymptote of this thing, really what we said was, okay, the vertical asymptote is wherever I'm dividing by 0, right? And so here, we need to find where x squared minus 7x minus 8 is equal to 0. And then pull those out of the domain. Okay. So I can use quadratic formula because I recognize that it's a quadratic and I want to solve what values of x make it 0. And so I have negative b, which is negative 7, plus minus the square root of negative 7 squared, minus 4 times a is 1 and c is negative 8 over 2 times 1. I need a calculator.
I got negative 1 and 8.
Show my work. If you did,
Showing up work sucks.
if you did use your calculator, I would want you to show it like this. So negative 1 and 8, and then just say from calculator.
Ah, okay. Got it.
Nice. You're allowed to do that. You're allowed to use your calculator functions. Totally fine by me. For me, I forget how to use it, and that's okay.
Is that negative 1 and 8 from calculator plus the quadratic formula that you wrote down? Or are you just chill with us just doing that?
Let's see. I want to see. So this would be enough if you're using your calculator. So I still want to see this, that you know kind of what you're doing.
Yeah.
And then you can just skip to it.
Okay.
Nice.
Those are the answers you get after you put it into your calculator, right?
Yeah, should be. Let's see. Or
Unless I don't understand the calculator.
by hand, what if I sneak attack this here? Copy. Weak. I get x is 7 plus minus 49 minus 4 times negative 8. Wait. Let's see. Oh, everyone's muted now. Maybe it was on purpose. The square root of 81 is 9. So we get 7 plus minus 9 divided by 2. So I get 7. 7 minus 9 is negative 2 divided by 2. You don't have to write that step, but and then 7 plus 9 is 16 divided by 2. Negative 1 and 8. So you can't just do it by hand, or you can use your calculator, kind of get used to using your calculator functions. That's cool too. My goal is for you to recognize that this is a quadratic and that you can use the quadratic formula, right? And then however you do that is fine. Nice.
So we do a times 3, we ended up factoring to get a quadratic. But that as well. Factoring up large.
Yeah, so sometimes, because we have ways of dealing with a quadratic, sometimes if it's bigger than a quadratic, then you're able to factor out and make it a quadratic. Yeah, so I think I have one of those. Not yet. Or maybe I just cut them. We're kind of gonna stick to quadratics. Okay, so what does this thing look like then? -1 and 8 means that I could rewrite this. Right? I've got f of x, so let me just do it beside here. Because otherwise, f of x was x squared minus 4 over x squared minus 7x minus 8. Knowing where that thing is equal to 0, okay, I know that if I let x be -1, then I get 0. Or if I let x be 8, bless you, then this overall thing should be 0. Okay. So what I can do is I can use these guys up here, and I can rewrite f of x, x squared minus 4, as x plus 1, yx plus 1. Because then if I let x be -1, -1 plus 1 makes 0. Okay. And x minus 8. Because then if I let x be 8, this term goes to 0. Right? And so the quadratic formula is good for finding where it becomes 0, but it's also good for factoring. And so here we can use, can I call this the quadratic, the QF? There, I've defined it. The quadratic formula to factor a quadratic. Yeah, let me just, good. Now what you can do to check your work, right, is you can expand this, you can feed your chickens, right? X squared minus 8x plus x minus 8. Then you can simplify it and you get back to x squared minus 7x minus 8. I always have a hard time factoring. And so for me, I really rely on the quadratic formula for factoring quadratics, because I have a really hard time thinking about what values add to -7 and multiply to -8. In that case, I could probably get there, but sometimes it's not as obvious, right? And so as long as you think about, okay, the two values of x that I found, -1 and 8, right? Each of them, not together, but each of them have to make 0, right? So I put in -1, doesn't matter what the other term is. 0 times anything is 0. So if I make this 0, then it doesn't matter what this term is. 0 times -9 is still 0. And then if I make this term 8, then it doesn't matter what this term is, right? 8 minus 8 is 0, so it becomes 0. Okay. So you could do the same thing to factor this x squared minus 4 if you wanted to. But we were only asked to find the vertical asymptotes. So I kind of took it too far. But from here, now that we have it in factored form, now it's obvious where this thing is going to be 0, right? At x equals -1 and x equals 8. So we have vertical asymptotes at x equals -1 and 8. I'll say and 8, and x equals 8. Let's do this one and up this down a little bit. This one's nice and factored already, right? And so that's nice. Makes it a lot easier. And so finding vertical asymptotes is much easier when the denominator is factored. Because now if I have g of x is 2 times x plus 3 divided by 3 times x plus 1 times x minus 2, I can see that if I let x be -1, I get 0, right? 3 times 0 times -3 makes 0. Or if I let x be 2, I get 0. 3 times 3 times 0 makes 0. So either way, therefore, their vertical asymptotes at x equals -1 and x equals 2. We can check in Desmos to see what happens or what it looks like. Now let's see if I can do something cool. Nope. Is it on this side? Nice. Okay. We have 2 times x plus 3 divided by 3 times x plus 1 times x minus 2. Oh, how do I undo? There. Phew. I just wanted a line at x equals -1 and at x equals 2. Looks like we nailed it. Make this bigger here. Come on. Wait. Let's see here. So for us, I'm really just concerned about, can you find vertical asymptotes? Do you know what makes them happen? And that would be when you have 0 in the denominator. Let's do this little guy. Find the vertical asymptotes. Now I'm going to pause it and give you 3 minutes because you've got your calculator functions to try it on your own. I'll pause this. Okay. So let's see here. What do you get with your calculator functions? if I want to force x squared plus 4x plus 3 equal to 0, I get x is negative b plus, bless you, plus minus the square root, oops, not 4 yet. B squared minus 4ac over 2a. I get negative 4 plus minus the square root of 4 squared minus 4 times 1 times 3 divided by 2 times 1. So I get negative 4 plus minus, and I'm going to deal with this 4 squared minus 4 times 3, which is 4, and then the root of 4, because I'm running out of, I guess I'll add a page. I'm cheap with my virtual pages, I guess. I get x is negative 4 plus minus 2 divided by 2. Oops. Negative 4 minus 2 divided by 2 puts me at x equals negative 3. And negative 4 plus 2 divided by 2 puts me at negative 1. So I can rewrite h of x. H of x is x plus 3 divided by x plus 3 times x plus 1. Okay. Now, we can cancel these. However, if you do, you're still going to have a vertical asymptote at x equals negative 3. Sort of. But what happens when we cancel these is we make a hole instead. And so here, we can cancel x plus 3 from the numerator. But when we cancel, we create a hole at x equals negative 3. But when we cancel, it creates a hole at x equals negative 3. So we can graph. So here, h of x simplifies to 1 over x plus 1. But if we graph these things, now let me see if I can remember which side. Phew. Delete, delete, delete. If I compare, bless you, x plus 3 divided by x. Maybe I shouldn't even use the factored version. Maybe I'll use that quadratic instead, the original function, which was x squared plus 4x plus 3. Now, where is x equals negative 3? It gets kind of tricky because what it doesn't show you. I'm trying. There, can you see it? I can't look up.
Yes, we do.
So it's undefined. So we have a hole at x equals negative 3. It's not going to be obvious if you're using Desmos, right? The difference between that function versus, so if I zoom out here, so we can look at this whole thing, and that function 1 divided by x plus 1, they're the same, except 1 over x plus 1 doesn't have that hole, so they're effectively different, right? They have the same shape because we use the same function and we just canceled, but when we cancel, it creates that hole. Right?
Would that still be an asymptote or would it just be a hole?
So in this case, let me screenshot this here. Do I have everything I want in there? Guess we'll see. So I'm gonna crop this up. So from here, we only have one vertical asymptote, and that's at x equals -1, right? Which we have from here as well. Right? But then when we cancel, that's what created the hole. And so here, notice the graphs look the same, except x plus 3 divided by x squared plus 4x plus 3 has a hole at x equals -3. I won't be able to take a screenshot, I don't think, because I would have to hold my pen and drag my pen. Can't do that. But both have a vertical asymptote at x equals -1. Both have a vertical asymptote at x equals -1. So what happens then is if you are able to cancel, that's cool, but just remember that it creates holes, right? It creates holes in your graph, just at those points, just at those values of x. Okay. I'm gonna switcheroo this and bring it up, bring it up here. So we can talk about horizontal asymptotes, because what's this?
Horizontal asymptote?
Nice. It is a horizontal asymptote, right? Because it has that similar behavior where it approaches y equals 0, but it never gets there. Okay? And so we're gonna have vertical asymptotes as well as horizontal asymptotes potentially. Okay? Now I'll put this little summary on your formula sheet, of course, so you don't really need to memorize it, okay? But how we determine where the horizontal asymptote is by the degree of the numerator and the denominator. Okay? So the degree is the highest power of x, right? So if the degree of the denominator, so in the bottom, is larger than the degree of the numerator, then you have a horizontal asymptote at y equals 0. So if we look at these guys here, let's snag copy this as an example. Oh, hello. Doesn't want to move. That's okay, I guess. The numerator has degree 1. The highest power of x in the numerator is 1. So the numerator degree is 1. Now the denominator degree is 2. Which means that the degree of the denominator is larger than the degree of the numerator. So we expect a horizontal asymptote at y equals 0, which is what we saw in our graph, right? That's confirmed by Desmos. So therefore, we have a horizontal asymptote, or HA, at y equals 0. And maybe I'll bump this up and just, which is confirmed in Desmos above. Add a page. If the degree of the denominator is less than the degree of the numerator, so you're dividing by something smaller than in the top, then there will be no horizontal asymptote. If the denominator and the numerator degrees are equal, then what happens, this is kind of the most interesting one, there's going to be a horizontal asymptote at the ratio of the leading coefficients, really relying pretty heavily on knowing that terminology that we introduced at the very beginning of chapter 3, right? And so the leading coefficients are the coefficients in front of your leading term, right? So let's grab the other two that we worked on the vertical asymptotes for. Boring. Still do it. Why is this one boring? Why did I say boring?
I have no idea.
It's boring because I see that even if I expand this, right, I get 2x plus 6, and then I get 3x squared, blah, blah, blah. I can keep going, but I don't really need to. I just need to know what the degree is, right? And so the highest value of x, or the highest power of x that I can get to here is x squared. Okay. And so I see that this is degree 1, and this is degree 2. Therefore, we have a horizontal asymptote at y equals 0, just like above.
Wait, could you go above?
Well, just like here that we had earlier.
No, could you go to where it looked like when it's graphed?
Yeah, did we graph that one? I don't think we graphed this one. Let's see.
Oh, okay.
We can graph it though. Why not? 2 times x plus 3 divided by 3 times x plus 1 times x minus 2.
I know backtrack, but by degree you mean like x squared, so it'd be 2.
Yeah, so it's the highest power of x that you can get to.
That looks like it doesn't have a horizontal asymptote with 0.
It yeah, because these guys, if I put a point here, right, this will never reach y equals 0.
Oh, okay.
And so this guy's never gonna get up there. That's okay. But these are behaving asymptotically at y equals 0.
I've seen 3 things like
That's the rational function. Let's see here. Rational functions are weird. never wants to paste anymore. So we have a horizontal asymptote at y equals 0. And we already found these vertical asymptotes. What was the first one that we looked at? Also boring. How about this one?
It's a ratio.
Mhm. Or maybe let's do this. Okay, that's okay. Find the horizontal asymptote, probably just one of this thing. Oops. Finally, I have a degree 2 over a degree 2. Which means I have that scenario. You want to make sure that you've listed all your polynomials from the highest degree possible and then decreasing, right? And so then you'll be able to see it relatively easily. But if the degree of the denominator is the degree of the numerator, then there's a horizontal asymptote at the ratio of the leading coefficients. I'm going to snag just this. However, the leading coefficients in this case is 1 over 1. So again, kind of more. So there's a horizontal asymptote at 1 divided by 1. And we had the graph of this thing, I feel like. Or maybe we didn't. Maybe I didn't bring in the screenshot. Okay. X squared minus 4. But I want that all in the numerator, so I'm going to use brackets, and then divided by x squared minus 7x minus 8. Whoa. Oh. Zoom. What if I draw a line at y equals 1? Neat. And we all already found the vertical asymptotes, but now I can't remember so long ago. -1 and 8. So if I draw lines at x equals -1, phew. And how about at x equals 8? Nice. Let's see if I can, there. I'll screenshot that and bring it in. If you had to guess, are there any holes?
Yes.
If
Maybe.
so, what did you cancel? I don't think we canceled anything.
There be, I don't know.
Kind of set you up, I guess. I didn't mean to.
Wouldn't there be a
Oops.
hole at like x equals 1? Where it's that weird cubic, inverse cubic function?
From here.
Well,
If I can cancel with x squared minus 4, so it has to multiply to -4 and add to 0. I'm gonna go with 2 and -2. But we had 1 or -1 and 8, so I wouldn't be able to cancel.
but I'm just thinking because if you go down, the horizontal asymptote crosses through one of the functions.
Oh,
Would that not be
here?
a hole?
That's okay, because the horizontal asymptotes are kind of weird in the way that it's only for the end behavior. So it's allowed to cross through kind of in the middle, but the end behavior is determined by the horizontal asymptotes.
Okay.
How do you turn that ratio into a? Oh my God.
This one here, oops. This one here at y equals, because the horizontal asymptote at a ratio, so the horizontal asymptote at y equals the leading coefficient
Oh, you just divide it. Oh,
over the leading coefficient.
I was gonna just do math.
No. So let's do something
Like,
spicier.
What, if it was 1/2, it'd be 0.5, y equals 0.5.
Yeah. Yeah, let's spice things up here. Find the horizontal asymptotes of f of x is 4x. Let's go crazy. X to the 3 minus 2x plus 1 divided by 13x to the 3 minus 4x squared plus 2x minus 4. I don't know, just making stuff up. What was my only criteria for making this up? My only criteria was same degree. Degree. I'll do it here. Degree 3 and degree 3. Everything else kind of fades away. So then we have a horizontal asymptote at y equals 4/13. I might have done something weird, but let's graph it and hope that it works out. 4/13 is roughly something bad. 0.307, 869. Can't stop.
This is going to be a very tight function.
I think so too. Let me put this all in the denominator. 4x to the power of 3. Step it down. Oops, step it down. Minus 2x plus 1. It's going to be a bit of a messy one. Divided by 13x to the 3. Step it down from the power. Minus 4x squared plus 2x minus 4. It's got some weird activity here.
Well,
That's
that-
okay. But if I draw a line
that's very
at
interesting.
y equals 4 divided by 13, phew.
So there would be a
The end behavior has a horizontal asymptote at y equals 4/13.
And there's a whole at negative 99 something.
It depends on if you can cancel stuff. I don't see an easy cancellation though.
My calculator can also do cubic functions.
Nice.
So I can
If you can do cubics, that's cool.
I don't know how it does it though. Do you know the cubic like the quadratic formula is the cubic formula?
I do not. I do not.
It's
I'm sure something exists though, but I don't know it. So then here, that's what that looks like. If we kept going more in calculus, then it would be more important for us to know kind of how do we determine this behavior, what makes this happen. But for us, I'm really only concerned about being able to find vertical asymptotes, horizontal asymptotes, and holes. Right. So for us, I wrote out kind of what to expect because there's also quite a bit in the textbook. So if you're reading the textbook and you get overwhelmed, it's okay. This is what I'm expecting of you. Okay. So I give you some rational function like this, just like we were doing, working with. And then I ask you to find the vertical asymptotes, potentially more than one, using the quadratic formula is kind of the most that I would get you to do, right? Sneaky on an assignment, maybe you have to pull out a common factor of X or something and then have the quadratic formula. Are there any holes? If so, where are they? And so being able to identify if there are holes. At that point, you've probably already factored the denominator, so then you'd be able to see quite easily if there are holes, right, if you're canceling. And then, is there a horizontal asymptote? And if so, what is it? Right? And maybe explain why. But remember, you'll have that summary of the degrees and how they relate to each other. And then, so it's your job to just know that if they're equal, then you take the ratios of the leading coefficients, just like we did. Okay, so kind of bare bones for that section, but that's what I'm expecting you to be able to do. Okay, any questions about that? That's the end of chapter 3. Can you believe that? So sad.
Are we moving on to chapter 4?
We are.
Hey, that makes sense.
We are. Chapter 4 might be my favorite chapter. I do love quadratic functions. I think they're really fun, but exponents and logs will always have my heart.
I want to learn about logs.
Let's do it. But first, a little bit of review. We did exponents. So first I want to just do, I'm calling it a review, although in a review in the sense that I kind of expect you to know these things. We've used them a little bit, but now we're going to be relying on these laws of exponents quite heavily. And so I expect you to be fluent with these laws. Yeah. And so it's worthwhile kind of reviewing them and spending some time here before we move forward. Yeah. And so I can't tell if you're stretching or if you have a question.
How do we know that a to the power of 0 equals 1?
Anything to the power of 0 is 1.
Yeah, but how do we know that?
Well, I'm sure the proof is like 4 pages long.
Could you prove it?
Me, no.
Oh,
Someone definitely got a PhD for proving it. It's
yeah, that
something,
makes sense.
it's always those simple things, like proving that 1 + 1 = 2 is a huge proof. And there's mathematical proofs of everything. So if you want to do proofs, there's a mathematical proofs course. I think you have to do calculus first, but
Not
then
here
you
at
can
the
do it.
college.
I think so, sometimes.
Huh.
Yeah, usually I think in the fall it's offered, but
That makes me funky today.
could be. Emphasis on the funky.
Yeah. A retirement thing to do.
Yeah, when school is free.
Yeah.
Oh, yeah.
School's free when you retire?
Yeah, once you're 65, school is free. Seems weird. Yeah. Yeah, just hang tight, guys.
That's 45.
Yeah, I don't know. I feel like there's probably some payoff in doing it earlier.
Probably.
Hopefully. Yeah. If we yeah, your earning power is not that great once you graduate, I guess. But you could do fun things like woodworking, or I don't know. There's like
Wait,
some cool classes.
what kind of job can you get from the Okanagan College's math group?
Well, the people in the data science program have to take the proofs course.
Really?
Yeah. It's more about mathematical reasoning and just kind of the structure and the formal structure of proofs.
Okay.
Much as in proofs, we're going to establish just kind of the parameters that we're working within. So if we let A and B be in the set of real numbers, positive real numbers, which means that A and B are in the interval from 0 to infinity, is what that means. I'm excluding 0 because there's a lot of conditions where A cannot be 0. Okay. Maybe I should include it and then let the exclusions speak for themselves. M and N, and I'm instantly regretting using M and N, even though it's kind of typical that you use M and N, but it's hard to hear the difference, is in the set of real numbers, which means M and N are in the interval, so are any values in the interval from -infinity to infinity. So A and B have to be positive, and M and N can be any number that you can think of, is what that's saying. I think we remember that if I have A to the power of N, then that's A times A times A times A N times. That's fine, I hope. Just as a fact, anything to the power of 0 is 1, as long as you're not taking 0 to the power of 0, because I'm pretty sure that's 0. 0 times itself none times. I don't know. What is, I think it's 0. 0 to the power of 0. Math error, it doesn't like it. Illegal math, I guess. Maybe that's why I was kind of floundering on what it was. Anyways, that explains why A can't be 0. It's illegal math. One of the things that I feel like I've relied on already is this little guy here. Is when I can rewrite 1 over a to the n as long as a isn't 0. Why can't a be 0? Well, I can't have a to the n, but then I would have 0 to the power of anything is 0, and so that's not in the domain, right? But as long as I have a not equal to 0, I can rewrite it as a to the negative n, right? And so this little guy, I can say something like 3 to the negative 2 is the same as 1 over 3 to the 2. And I'll give myself a little bit more space here. For all of these properties or these laws, we move between the two and whatever is convenient, right? And so you need to be able to rewrite this negative power as something in the denominator, but also be able to rewrite something in the denominator as just a negative power. Another go-to move of mine, at least, if I have to use my calculator to calculate the nth root, then I use a to the 1 over n. So if I have something like, I want to take the 14th root of 3, 3 is kind of I guess my default a. That's not on purpose. But on your calculator, what are you going to do? You're going to do 3 to the power of 1 over 14 to calculate that root. So that's a sneaky trick that you can use. So the 14th root of 3, 3 to the 1 over 14, 1.081, blah, 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 blah. So then you're able to calculate it. Kind of in a similar way. Now let me.
There's an option on the calculator doesn't really punch it in like the 14th or 14th.
Is there? I only have the third root and the. Oh, there it is.
Yeah.
Yeah, there it is. So then you can do 14 root 3 and get the same thing. That's because we have these fancy schmancy engineering calculators.
Yep.
Very fancy. Some of these rules are kind of redundant because they build off of other rules. For example, rule number 5 says that a to the m over n, whoops. I can rewrite this, and I'm going to do it in a different order. This I can rewrite as a to the power of m, whoops, to the 1 over n. And we haven't introduced that rule yet, but that's by this rule, by rule number 8. If I have something like this, m times n in the power, then I'm allowed to separate those out. And so the rule says that these guys just multiply. And so really here, by rule number 8, I can rewrite this. I'll even add another step here. A to the power of m times 1 over n is the same as a to the m to the 1 over n. Which I can then rewrite as the nth root of a to the m. But you can also move the other way, right? If you have the nth root of a to the m, then you can move it back to just some exponent. Another one that I know I've used in the past is this little guy. Let's see here. Let's see if I have a color I can use. Pink, maybe. Rule number 6 says that a to the m times a to the n, I can consolidate as a to the m plus n. Notice that it has to be the same base, right? So if multiplying the same base, we can add the exponents. Add a page here. This down. So I do have some problems for us to work through, but we need to establish these laws first. Do you need rule number 7? Not really. Rule number 7 is kind of redundant. Why? Sort of redundant. Because it's a combination of rule 6 and rule 4. A combo of rule number 6 and number 4. Why? Well, I can rewrite a to the m over a to the n is the same thing as a to the m times a to the negative n. Right, I'm allowed to bring that a to the n upstairs by making that exponent negative. But now I have the same base. And if I'm multiplying the same base, I'm allowed to add those exponents or those powers. And so then I get a to the m plus negative n. But subtraction is just a special case of addition. And so then I get a to the m minus n. So you don't really need it, but here's the proof, relying on the previous rules, of why a to the m over a to the n becomes a to the m minus n. Or if you're dividing, you remember that you subtract the powers. I actually like to have as few rules as possible. I don't like to have all of them spelled out for me because I prefer to just build them out as I need them. But I know that's not everyone's flavor. We've already seen rule 8. But rule 8, right, is if you're multiplying those exponents, then you're allowed to separate them or combine them, right? And so here you can pull out a common multiple if you need to. So I don't know what to write about this one. This is just a fact, I guess. Yeah, what can I say about this little guy? There's nothing to say, just a fact. There. It's a fact. How about a times b to the power of n. Now it's important that you bring this n inside. This only works for multiplication and division inside, right? We know that that's not true for a plus b, right? And so here, notice that this distributive property is what it's called.
Would we get these on a formula sheet for a test?
I wasn't going to, but I can. Okay, you can have them on your formula sheet. I'll be nice.
Thanks.
Should let us go early too.
Thanks.
Do you have a question?
Yeah.
About the math assignments,
Okay.
not about this. Yeah.
Okay. So here, note the distributive property, which is just bringing the exponent inside. Only works on multiplication and division. Only works on multiplication and division. Why? Because if you have a plus b to the power of n, we know that that's a plus b times a plus b times a plus b n times by property number 1. Right? Which is not equal to a to the n plus b to the n. So I never want to see that. It only works on multiplication and division, but division is just a special case of multiplication, right? Just like subtraction is a special case of addition. So here, if we have rule number 10, a over b to the power of n is the same thing as a times 1 over b to the power of n, which is a to the n times 1 over b to the n. I guess I still need that rule, 1 over b to the n, or I can rewrite this as a to the n times b to the negative 1 to the power of n. But then I can combine b to the negative 1 to the n by property 8, I think it is. This becomes a to the n, b to the negative 1 times n by property 8, which I can then say is a to the n, b to the negative n, which you could just rewrite as a over b, or sorry, a to the n over b to the n by property 4. I don't expect you to name the properties as you go, but I think it's a good exercise to kind of think about what properties you're using, right? And then that'll kind of guide you along. So using those properties, let's do, oh, you can't see when I'm grabbing and copying, so that's kind of confusing. Let's work through property 11. If I start, I can start on either side and work my way to the other side. I'm going to start on the left side and move my way towards the right-hand side. But you can try it the other way. So here, A over, and maybe I'll use a different color, A over B to the negative n. I can rewrite as A to the negative n over B to the negative n. And I'm going to name the property, which was that previous property, property 10, I think. This one. So I can take a power and I can distribute it across the numerator and denominator. And so here by number 10, then A to the negative n, I can rewrite as 1 over A to the n. And B to the negative n is in the denominator. So what I can do is I can multiply this by B to the negative n. And when I negate that negative n, it makes it positive in the numerator. And this is by number 4. But B to the negative n is just B to the n. And so I get 1 over A to the n times B to the n. That's just negatives. And now technically I have a fraction over a fraction. B to the n over 1. You can imagine that. So now a fraction times a fraction is just B to the n over A to the n. And now I can use which property? I can use property 10 in reverse, right? And I can pull out this common power of n and put it all on the outside of the division. So then this becomes, oops, this becomes B over A to the n by number 10. Which is this rule here. So you don't really need the rule as long as you know the other kind of core rules. Ones that I rely on quite a bit. Rule number 4, number 10, 8, kind of thing. What about this last one? Let's grab this here. Copy. This is pretty similar, except now I don't have the same power, right? So I can't use rule number 10 and pull it all outside, but that's okay. It's very similar to the previous, where I have A to the negative n over B to the negative m is 1 over A to the n times B to the negative m, which gets me to the B to the m over A to the n. Let's do a little warm up. if you have to simplify this thing, first thing you're gonna look for is, do I have the same base? If I have the same base, I'll be able to consolidate all these exponents. So I have to simplify this. There's a couple of different ways I can do it, right? I could bring a to the 7 upstairs. I use that terminology. It's not technically correct, but I bring the denominator upstairs by negating the power, right? By rule number 4, I guess. And so that's something I can do. A to the 4, a to the 8, a to the negative 7 by number 4. Now they're all in the power and they all have the same base. And so I could do these incrementally, or just recognize that, okay, if I'm multiplying the same base, then I can add all those exponents, right? And so this, you could do a to the 4 plus 8 times a to the negative 7. Or I'm just going to skip straight to it and do a to the 4 plus 8 plus negative 7. And usually I wouldn't write the addition, but it's our first kind of stab at this. And so I'll write the adding the negative. Usually I would just skip to a to the 4 plus 8 minus 7. 4 plus 8 minus 7 is 5. And that's as simplified as we can go. So we did it. What if you have to simplify this thing? For me, it's always tempting to distribute and expand, but this is going to get huge pretty quick, right? Because 1 plus I to the power of 3, just that is going to be 1 plus I times 1 plus I times 1 plus I. You got to feed all those chickens. And then never mind the 9, 1 plus I. So what you're going to do is you're just going to treat the 1 plus I as one thing, right? So now, treating 1 plus I as one thing, you have the exact same scenario as you had up here, right? You have a to the 3 times a to the 9 divided by a to the 6, for example. So this you can rewrite as 1 plus I to the 3 times 1 plus I to the 9 times 1 plus I to the negative 6. Bringing that upstairs. Which would simplify to 1 plus I to the 3 plus 9 minus 6. 3 plus 9 minus 6, 6. I'll make a note here. Treat 1 plus I as one thing. And that'll make it easier. Drop these down. What if you have to simplify this? This one's sneaky. because you have the addition. Now with the addition, there's nothing that we can do really, but we can bring that 4 inside, right? So here, be careful with addition. Because there's nothing we can do really. So we get a to the 3 plus a to the 5 to the power of 4 divided by a to the 4. If you had to bring all these kind of onto the same level, what could you do? You could write a to the negative 4, putting it out front, kind of snazzy like that. Doesn't matter. A to the 3 plus a to the 5 to the power of 4.
Both would be okay in answer.
I might say something like simplify by bringing all values into the numerator. So in that case, I would want it like this, but I would specify that I would want them all in the numerator. What if you had to simplify this little guy? Oops. X plus 3 to the 5 times 3 over 2. X plus 3 we can't touch, that's one thing, right? But we do know that I can multiply 5 times 3 over 2 and combine these as one exponent. And so what I get is I get x plus 3 to the power of 5 times 3 over 2. I'll write it out. Technically 5 over 1. A fraction times a fraction, you can just multiply across. X plus 3 to the 15 over 2. And that's as far as you can go. I'll even add this here because you've got addition in both. Addition, subtraction, you can't do anything with. For the last one, because I sense you're keen to get to your lab.
Yeah. Oh,
We'll do this one. We need to be careful that you have the same base, right? Otherwise you can't collect your exponents. And so what I would do is I would personally bring the a and the b up to the numerator. In fact, I could do the -2, but I could also just take 6 divided by -2 and simplify it here. The only reason I'm allowed to do that is because I'm multiplying all these values together. So first things first, I can do 6 divided by -2 times, right? Just kind of split it out. And then I can rewrite this as a squared times b over a times b squared. I'm allowed to rewrite a multiplication like that. 6 divided by -2, I'm going to go for -3. And then what can I do? Now, depending on kind of how comfortable you are with canceling, right? You might say, okay, I've got an a squared here and an a multiplying in the denominator. Because I'm just multiplying all around here, I'm allowed to cancel this a squared with this a, but then that a goes away. Now, the reason you're able to do that is because if you bring this a to the numerator, you get a squared times a to the negative 1, which is just a to the 1. Right? And so here times a squared b times a to the negative 1 times b to the negative 2. Grouping your a's and your b's, you get negative 3 a squared times a to the negative 1 times b to the negative 2. I only use the brackets to emphasize that I need to collect the same bases. Negative 3 times a to the 2 plus negative 1, b to the 1 plus negative 2. I get negative 3 times a to the power of 1 times b to the negative 1, or negative 3a over b. You might have looked at this and gotten here on your own, just kind of by canceling, right? Recognizing that, okay, I'm just dividing and multiplying, so I'm allowed to cancel. But what you are technically doing is these laws of exponents. So you're allowed to go from here to here, that's fine. But I just wanted to show you that you are relying on these exponent laws, even though you don't think about them anymore. Okay. So on Thursday, we'll start chapter 4. But you can memorize those exponent laws or work through those for some practice. I'll see if I can rustle up some more practice problems. But if you have any questions, let me know. Otherwise, I'll see you on Thursday.